All right, hello everyone. Welcome to my channel. This is a channel that is dedicated toward educational empowerment through learning about uh, mainly theories of everything, all encompassing theories that you can apply to every aspect of your life. Most of them have been authored by people who you've never heard of before. People who spent their whole life working on something and never received any credit, never got any money, but they kept plugging away anyway. And before their life ended, they put together a magnum opus that inspired me to, improve my life through their work, and I'm trying to pay them back a little bit by spreading the knowledge of their findings um, to other people so that they don't end up on the scrap heap of history, and so other people can have some valuable perspectives in their life. Um, and a lot of times, these people, we're trying to uh, of we're digging into a new language. They had to come up with new words to describe what they were finding. And so a lot of times it's very difficult going. A lot of times they're very difficult to understand. They're not all great teachers. In many cases, they're very good writers. But the information is there, but it needs to be dug out. So, in a certain sense, I'm also trying to translate their work in a way that is more accessible to other people, at least in some cases. I think that may be true in this case. Today, we're going to do our 219th video on the reciprocal system of theory, which is a theory that was first authored by Dewey B. Larson back in the 20th century. He wrote many books and quite a few articles, did a lot of talks on his reciprocal system. The basic idea behind the reciprocal system is that we live in a universe of motion. The universe is not made out of matter, it's not made out of energy, it is made out of motion. Matter and energy are merely two different kinds of motion, and as well as a whole lot of other scientific entities, quantities such as pressure and capacitance and fluidity and viscosity and speed and acceleration and force and matter and energy and um, electric current, electric charge, magnetic flux. These are resistance. These are all different kinds of motion, and they're identified generally by a fraction that has space or time as the numerator and time or space as the denominator. That basically sets up a reciprocal relationship between space and time. Now, it is a little bit more complicated than that, hence the reciprocal system of theory, the title of Larson's theory. It's a little more complicated than that because space has, or time and space have their coordinate aspects. Both of them are multidimensional, three or more dimensions, XYZ coordinates in space. But there is also something that's called coordinate time, which would be, the three different letters in coordinates in time. Then there's also the scalar or clock aspects of space and time. We generally recognize that time is progressing. Time is always getting later and later and later. That is the flow or the progression of time. But as Larson calls it, clock time. But there's also clock space. The clock is space is always getting farther and farther and farther apart, but in no particular direction. It's what Larson calls a scalar motion, a motion with a magnitude but no particular direction. And so there is also what you call the discrete unit postulate. Time and space both come in discrete units. There is a minimum unit of space and a minimum unit of time. And below that, you don't have space or time. You only, so these units are very small, but they only come in chunks. There is no continuity. There is a minimum size of a unit of space and a unit of time. And 1 unit of space in 1 unit of time is the speed of light. So the speed of light is really the midpoint of Larson's universe, whereas in Einstein's universe, the speed of light was the maximum speed of the universe. But that's because Einstein didn't recognize an entire half of the universe. In Larson's system, the speed of light is the midpoint between two separate halves of the universe, what Larson calls sectors. There is the material sector, the sector that is moving slower than the speed of light. That is what we are accustomed to and that we make our measurements and our observations from. But then there is also the cosmic universe. This is the universe that is moving faster than the speed of light. And this universe is also interpenetrating our reality, but we can't see it. But maybe we can think it, or maybe we speak it. But who knows what the true nature of the cosmic universe actually is at this point. We're just delving into it right now. But what you can see is that we can understand a lot of things about the cosmic universe because of the reciprocal postulate. So what goes on in the material sector is exactly the same as what's going on in the cosmic sector, except that the roles of space and time are reversed. For example, in the material sector, you have coordinate space, 3 dimensions of space, and clock time. The clock is always getting later and later and later. But in the cosmic sector, you have coordinate time, 3 or more dimensions of time, and you have clock space. Space is always getting farther and farther and farther apart. That shows that one sector is really the inverse of the other, with space or time inverted. Okay, now we're looking at Larson's 1979 book here called Nothing But Motion, which is generally on atomic physics. For Larson, an atom or matter is a combination of several different kinds of motion. First, you have a photon that's at the core, 2 photons that are at the core of atoms. And those photons are simple harmonic motions or wave-like motions, which are the result of a combination of 2 separate motions, which we will get into very soon in future videos. But we'll just say photons are a wave, and then a wave-like motion. And then once you have those 2 photons, you have to rotate them in 2 or 3 different ways, and that is what makes up an atom. And then obviously a cosmic atom is the same thing, but with the space and time reversed. So with a material atom, you have a wave in time that is rotated in space. With the cosmic atom, you have a wave in space that is rotated in time. Cosmic atoms are what legacy science calls antimatter. And a cosmic atom that comes into the material sector, crosses that speed of light boundary into the material sector, is what is usually called a meson or cosmic ray. And Larson went through all that in previous chapters. We're looking at chapter 18 of this book that's called Simple Compounds. And so a compound is a combination of 2 or more different atoms. So this is the next level of building up a universe, is to figure out what's going on with a compound, a molecule, a combination of atoms. Okay, here he's talking about valence. So we're just going to read from here. Don't be too distressed if you don't understand everything in here. You probably would need to listen to all the videos in this series, but you can pick up a few bits and pieces and kind of hear how Larson thinks. And then, that's really how you build your understanding of the reciprocal system, is, one brick at a time, one concept at a time. Things gradually make a little bit more and more sense. You can see how Larson is consistent in the way that he thinks and the way that he builds up his theoretical universe. That is what Larson does, is he starts with those initial postulate, especially the initial postulate about the discrete units, the coordinate space and time, and the clock space and time. And then he basically goes through a process of deduction. If this, then that. If this, then that. And he builds up a theoretical universe, which he then eventually attempts to match with the so-called actual universe, or the universe that the scientists have observed and measured, and to come up with correlations. Okay, when this certain thing popped out of my theoretical universe, what do the scientists call that? So when he comes up with cosmic matter, he recognizes that the material scientists are actually calling it antimatter. Okay, it should theoretically be possible for valences to be diminished by orientation in the manner shown in Figure 2, but it is doubtful that if any stable compounds are actually formed on the basis of diminished electric valences. The reason for their absence is not yet understood. The magnetic valences are both enhanced and diminished. Okay, just for a little bit of background, in Larson's notation, every atom has three numbers, A, B, and C. A and B are the two magnetic two-dimensional rotations, and C is the optional electric rotation, one-dimensional. And those three numbers make up, every atom has its unique, every element has its unique three-number set. And valence basically is established to balance. So like two compounds will balance one of those three numbers out. So there's a magnetic valence and there is an electric valence. Okay, the magnetic valences are both enhanced and diminished. That's kind of a technicality. So he went through that just earlier in this chapter. Either the primary or the secondary valence may be modified, but since enhancement is in the direction of lower probability or higher numerical value, the number of common compounds based on the enhanced magnetic valences is relatively small. Diminishing the valence improves the probability, and the diminished valence compounds are therefore more plentiful in the rotational groups in which they are possible, those with primary magnetic valences above 2. Although the list is still very modest compared to the immense number of compounds based on the first-order valences. As indicated earlier, one component of any true chemical compound must have a negative displacement of 4 or less. I'm sorry, something's going on. I'm trying to scroll here. Okay. As indicated earlier, one component of any true chemical compound must have a negative displacement of 4 or less, as it is only through the establishment of an equilibrium between such a negative displacement and an appropriate positive displacement that the compound comes into existence. The elements with the required negative displacement are those which comprise division 4. And it follows that every compound must include at least one division 4 element, or an element which has acquired division 4 status by valence enhancement. So division 4 are the elements that are over on the far right side of the periodic table with a valence of 4 or less. Those on division 1 are all the way on the left-hand side of the periodic table with a valence of 4 or less. And then division 2 is basically everything that's on the left-hand side that is not in division 1. And then division 3 is everything on the right-hand side that is not in division 2. Those with the valence of 4 are in both division 1 or 2 or division 3 or 4. So every compound must include at least one division 4 element, or an element that has acquired division 4 status by valence enhancement. If there is only one such component, the positive-negative orientation is fixed, as the division 4 element is necessarily the negative component. Where both components are from division 4, however, one normally negative element must reorient itself to act in a positive capacity, and a question arises as to which retains its negative status. The answer to this question hinges on the relative negativity of the elements concerned. Obviously, a small displacement is more negative than a large one, since it is farther away from the neutral point where positive and negative displacements of equal magnitude are equivalent. Within any one group, the order of negativity is therefore the same as the displacement sequence. In group 2b, for instance, the most negative element is chlorine, followed by sulfur, phosphorus, and silicon in that order. So that's elements 17, 16, 15, and 14. This means that the negative component in any division 4 chlorine-sulfur combination is chlorine. And the product is a compound such as SCl2 as opposed to CLS or Cl2S. On the other hand, the compound P2S3, phosphorus 2 silicon 3, is in order, as phosphorus is normally positive to sulfur. Where the electric displacements are equal, the element with the smaller magnetic displacement is the more negative, as the effect of a greater magnetic displacement is to dilute the negative electric rotation by distributing it over a larger total displacement. We therefore find chlorine trifluoride, ClF3, and iodine tribromine, IBr3, but not FCl3 or BRI2. The magnitude of the variation in negativity due to the difference in magnetic displacement is considerably less than that resulting from inequality of electric displacement, and the latter is therefore the controlling factor except where the electric displacements are the same in both components. On the foregoing basis, all elements of division 1, 2, and 3 are positive to division 4 elements. The displacement 4 elements on the borderline between divisions 3 and 4 belong to the higher division when combined with elements of lower displacement, and when elements lower in the negative series acquire valences of 4 or more through enhancement or reorientation, they also assume division 3 properties and become positive to the other division 4 elements. Thus, chlorine, which is negative to oxygen in the purely division 4 compound OCl2, is the positive component in Cl2O7. Similarly, the normal relations of phosphorus and sulfur as they exist in P2S3 are reversed in S3P4, where sulfur has the valence of 4. Hydrogen, like the displacement 4 members of the higher groups, is a borderline element, and because of its position is able to assume either positive or negative characteristics. It is therefore positive to all purely negative elements, division 4 below valence 4, but negative to all strictly positive elements, division 1 and 2, and to the elements of division 3. Because of its lower magnetic displacement, it is also negative to the higher borderline elements such as carbon, silicon, etc. The fact that hydrogen is negative to carbon is particularly significant in view of the importance of the carbon-hydrogen combination in the organic compounds. And Larson is going to, in the next chapter, get into some of these organic compounds. I think that we are going to forego that here, at least for a little while, and we're just going to try to get through this chapter and then move on to some other stuff. We might just discuss, I think there are 3 or 4 more chapters to this book, but I just see that we're kind of getting into the weeds here. You really have to kind of have the periodic table in front of you as you look at these different things and you understand how chemical bonding occurs in Larson's system. And the next chapter is on complex compounds, so we're going to get even further into the weeds. And I'd rather just go back and look at and cover some stuff that is more basic, maybe in other fields. And so I think we're just going to trudge through the rest of this chapter, which is just a few more paragraphs, and then move on to some other stuff, or at least summarize the end of this book and then move on to some other stuff. So stay tuned for that tomorrow. And thanks for tuning in. Have a great day.